Hello everybody. Welcome to this last video in this series of videos on probability. This one is on geometric probability. So this is a good review of a lot of the probability stuff we've done, plus some of the area stuff that we did before school closed. Okay. So if you're following along with me in the probability packet, I'm actually skipping number 1 on this page, because normally I would do that as a warm-up, and I want to get into the main ideas here of geometric probability. So I'm starting with number 2. So I'm going to tell you just very briefly what geometric probability is, and then we're going to see it in action with some examples. So geometric probability is pretty much what it sounds like. It combines probability ideas, which is like part divided by whole, with geometry ideas like area. Okay, so probability, which I'm hoping that you know by now, is basically part divided by whole, right? So the part that we're looking for divided by the total. We've been doing that with Venn diagrams, tree diagrams, two-way tables, lots of different things. But we can also do that with areas of shapes. One second, y'all, I got something in my eye. So we can also do that with areas of shapes, right? If you have like a small shape inside of a big shape, we can figure out, okay, what percentage of the total area does that smaller shape take up? And that's what we're going to do here with these geometric probability problems. This is actually how people who design dartboards figure out what point values to assign to different areas, because the harder things are to hit, right, the smaller the area is, the more points you want to give people. Okay, so I'm going to do an example for you here with this dartboard, and then there's 4 other dartboards on the next page that you can try out. So watch my example here, and then I would try the examples on the next page. Okay, so in my lovely picture here, I have this dartboard. It's square and it has 2 circles inside of it. Okay, so what that tells me is that I'm going to need the area formula for a square, which is base times height, right? Square and a rectangle, base times height. And I also need to know the area of a circle. Formula for that is pi r squared. All right, so let's take a look at the problem here. So this problem says that the dartboard is, the target here is on this square dartboard that's 15 by 15 inches. So that's the side lengths. Small circle has a radius of 2. The large circle has the same center, so it's not like off center or anything, and has a radius of 6. Okay, if you throw a dart and it lands in the shaded circle, then you win a big prize, like the grand prize. If it lands in the the larger circle, so inside this ring here, you get a smaller prize. And then obviously if it lands outside of the target, then you don't win anything. So let's go through these steps and see if we can calculate some of these probabilities. So very first thing, whenever you're doing geometric probability problems, if it's not already labeled for you, you should label the problem. So let's label with the information that we have. So they told us in the problem that the side lengths of this square are 15 by 15. Okay, so 15 by 15 inches. Then I know that the radius of the circle in the middle is 2 inches. And then I know that the radius of the big circle, so that's this whole thing right here. So not just this part, this whole thing is 6 inches. Okay, so there are 3 shapes here. In order to find any areas, in order to find probabilities, we have to find areas first. So let's find the area of these 3 shapes here. So my area of my square dartboard is, so the area of a square is base times height, which is 15 times 15, and that is 225. And then my unit on there is inches squared, right? So pretty easy, simple enough, hopefully. Okay. Part C says I want to find the area of the shaded circle. So that's my small circle right here. So the area of a circle is pi r squared. So that's pi times, and then my radius is 2. So pi times 2 squared, that's 4 pi. So remember when we did stuff with area, I was telling you that you can leave area in terms of pi. So you could leave your answer like that. I'm going to convert it to a decimal value just because it's going to make doing the division, like in figuring out what the probability is, it'll make it a little easier later. So we're not having to deal with pi. So 4 times pi is 12.57. Okay. And I rounded, obviously, because the decimal goes on forever. And then my unit is still inches squared. Okay. So up to this point, we've seen all of those things before, fairly simple. Part D is a little bit trickier because it's asking me for the area of just the outer circular region. So not the whole circle, not this whole big circle, but just the ring part, right? If you think of it like a donut, right? I'm trying to find just the area of the donut without the hole in the middle. So what that means is I have to find the area of the big circle. Right? I have to find the area of the big circle, and I need to subtract the area of the small circle. Right? That it's literally like if you have a donut, you're taking the hole out of the middle, right? I have to subtract it. So I know the area of the small circle. I found that already, but let's find the area of the big circle. Okay, still pi r squared, but it's pi times, and my radius is 6 squared this time. So that's 30. Sorry, everybody. Lost track of my numbers here for a second. So that's 36 pi. Okay. Which is, if you do 36 times pi in your calculator, you get 113.10. So now I need to do this. Give myself a little like barrier here. Now I need to do this, okay, which is, so 113.10 minus 12.57, and figure out what that is. You could also do 36 pi minus 4 pi. So I'm going to do that over here. You could do 36 pi minus 4 pi and just subtract these, which is 32 times pi, and then figure out what that decimal is. You could do the exact same, like do that process, and you would get the same answer. Okay, so when I do all of this subtraction, I get 100.53, and then my unit is inches squared. All right, so now that we've done the area part, we have to do the probability part. So the probability is still, it's part divided by whole. Right? So this probability is still part divided by whole. So the part that I'm looking for the grand prize is the area of this small circle, because in the problem, that's what they said. If you throw a dart and it lands in that shaded area, then you win the grand prize. So the part comes from part C. So this is, it should be the area of the small circle divided by the total area, which is the area of the square. So that's 12.57 divided by 225. And that's something I'm going to have to do in my calculator. So let me do that really quickly. So I have 12.57 and I'm going to divide that by 225. And when I do, I get 0.056. Typically with probability, it's a good idea if you can to give me 3 decimal places. Usually a good idea. So here is your probability. Makes sense that it would be small, right? Because if it's going to be a grand prize, you don't want the probability of winning to be really, really big, because that's really expensive for the people who are, running the game at the county fair. Okay, so this is a 5.6% probability. If you're following along with me and you did it slightly differently in your calculator, like I did this, the 12.57 divided by 225 without rounding. So I took the exact number that came from multiplying by pi, so it had lots more decimal places, and then divided that by 225. I didn't round. So if you rounded, your answer may be slightly different than mine, but that's okay. It's just due to rounding error. All right. Let's look at this last one here. So probability that we win the smaller prize it's the area of the ring, which is what we found in part D. And again, we're dividing by the area of the square. So the area of the ring was 100.53. That 5 looks ridiculous. Divided by 225. So that's another thing that you're going to have to do in your calculator. And like I said, I'm doing this without rounding. So your answer may be a little different than mine if you are rounding this number at the top in the numerator. So when I did this in my calculator, I got 0.447. So you have a 44.7% chance of winning. Pardon me. 44.7% chance of winning the small prize. So that in essence is geometric probability. So we're just combining a lot of the stuff that we did with area with this idea of part divided by whole. So it's a good review and combination of a lot of those things. Okay. So I'm not going to work out and explain every single one of these DART problems, but I will set them up for you so that you can try them on your own. So here, there's 4 different dartboards, and they're trying to figure out which one is going to make the probability of hitting the bullseye, which is the shaded portion. I want to make that smaller, right? Or as small as possible. Okay. So a couple of things you're going to need. Obviously, you're going to need some formulas here. So the area of a square is base times height, which you need that for part A and part C, right? You need it for this one and this one. Then the area of a circle is pi r squared. And I'm going to tell you right here, this 1.5 is the radius. Okay, so 1.5 is the radius. So you're going to need this for part A. You're going to need it for part C. And you're also going to need it for part D. And then lastly, we have the area of a triangle, which is base times height divided by 2. So you're going to need that one for part B, and you're going to need it for part D. The one thing I will say about these problems that have the triangles on them, you will need to use the Pythagorean theorem for part B and for part D. So you would do something like this: 3 squared plus b squared equals 5 squared. Or if you remember, this is a 3, 4, 5 triangle, right? So remember the shortcut. And then you'll also need the Pythagorean theorem to figure out the height of this equilateral triangle right here. So you can do that. So remember, when you draw a height in an equilateral triangle, it cuts the bottom in half. So this is 6. So this would be like 6 squared plus b squared equals 12 squared, right? And you can go through and figure out what the height is that way. Or you can go back to, remember our special right triangles, the 45, 45, 90, and the 30, 60, 90. This is a 30, 60, 90 triangle. So you can see if you can figure out the height using the ratios if you want. Okay, and then my very, very last problem here that you don't have all the information for is this one. Again, you're going to need the Pythagorean theorem here to figure out what this missing height is, or base, sorry, of the right triangle inside that circle. So 8 squared plus b squared equals 13 squared. We want to try to figure out what that value is. Okay. All right. So I'm going to pause the video here. And I advise you to do the same. So go ahead and pause the video, pick a couple of these to try out. And when you see me again, you're going to see the solutions on the screen so that you can check your answers. All right. All right, everybody. So I hope you had a chance to try those 4 problems to figure out what the probability is of the bullseye for each one. I'm not going to work through the whole thing. Like, I'm not going to talk through all of them. But I'll give you a general overview, like the steps that I used in order to solve these problems. So for all of them, I figured out what the area of the shaded shape was first. So like in part A, it was this circle. In part C, it was this square, etc. If I was missing any values, like in the bottom 2, I was missing the base of the shaded triangle for both of them. So I used the Pythagorean theorem, which I set up for you here and here. I didn't show you the whole thing of how I worked it out. I'm hoping that you know how to do the Pythagorean theorem by now. So I used Pythagorean theorem to find any values that I was missing to figure out what the areas were. So I found missing values, then I found the area of the shaded shape, and then I found the area of the big shape. So the area of the square in part A, area of this triangle in part B, area of the circle in part C and part D. And then I divided the smaller area by the bigger area. So for part A, I got that the probability for bullseye was 0.049, so 4.9%. For part B, which is down here, I got 0.096, so 9.6%. For part C, I got 0.020, so 2%. And for part D, I got 0.091. So if I was to pick a dartboard, right, that minimized the probability of hitting the bullseye, I would definitely pick C. It has the smallest probability. Couple of things I want to point out for you here. One is that none of these pictures had units in them. So remember, if you don't have units in the problem, you don't have to give units in the answer, which is why I didn't write any units when I was calculating areas. All right. And then another thing I want to point out to you is that even though the bullseye area in part D looks bigger than the bullseye area in part B, you get a smaller probability. So this is a lesson to be careful about your using your pictures to make your choice, right? You have to actually show that the math works how it's supposed to, right? So like, for example, if the problem had only been these bottom 2, so if I had eliminated the top 2 and it had only been this dartboard and this dartboard, just visually, I would probably pick this dartboard because the shaded area looks a lot smaller, right, than this one. But when you actually calculate the probabilities, the probability of hitting this bullseye in part D is smaller than the probability of hitting the dartboard or hitting the bullseye for part B. So the pictures are not always to scale, not always what they appear. So make sure that whatever choice you make, you can support it with the math, which is a good thing to point out no matter what kind of math you're doing, right? Pictures are not always to scale. So good idea to, or at least check, right? Don't make your decision solely based on the way the picture is. Support it with the math, all right? So that's pretty much the end of this video. If you would like to try number 4, if you're curious about it, go ahead and try it on your own. And then if you want me to check it, feel free to send me an email or a message. I'm happy to do so.